Thanks everyone for joining and getting off to a great first start. I feel like I'm in sort of an ideal position in the week because I've been able to sit back there for long enough to snap a few pictures of people as they're giving their talks and thought about how I might pick up on a few threads of what we've seen so far this week and hopefully stitch a few things together in a way that we can use and better understand. So we're going to be thinking about reactive transport today. We're going to be doing some fundamentals of reactive transport, and in particular, because several of my colleagues are going to do more fine-scale, pore-scale work later, I thought we'd think about big-picture reactive transport, as well as some of the ways in which we get these reactive transport models to function. So, disclaimer, straight up in front, there's going to be a little bit of chemistry. I promise you I will do everything I can to make it so that you enjoy the chemistry and come to appreciate that, in fact, it's something that we can all work with pretty easily. Okay, so I will learn how to, there we go. All right, so it's a long enough talk that I thought we deserved a little bit of a roadmap. The first thing we're going to do is we're going to revisit what I think has started to orbit in the workshop so far this week, this concept of characteristic timescales. And we'll do this for a very specific reason, what I think is a very undervalued question in your professional career. Do I have to? When you say that, people are usually like, what do you mean, does she have to? Of course she has to. Do I have to is a very valuable question to ask. We don't want to design and execute a complex model for a system that simply doesn't call for it. So we're going to use these basic ratios of timescales, how fast something is chemically reacting versus how fast it's transporting, to ask when and where do I develop a reactive transport model. The next thing that we're going to do is think about situations in which we want to consider multiple chemical species in a given system. They're interacting with each other. They're also transporting. They're also subject to all the variety of different complexities that we've started to hear about in these lectures of mixing and diffusion and dispersion. All kinds of different behavior that we want to try to encapsulate into one framework. In other words, what is this C that everybody's talking about? We're going to get through that part. It's going to be okay. It'll be fun, maybe. We'll see. Then we're going to step back into a beautiful outdoor landscape. We're going to think about a real watershed. We're going to think about an upland system in which bedrock is being actively converted into soil, in which rainwater is being actively converted into streams and groundwater. And we're going to think about how we would build this kind of model for a system like that. So we need to get going. When do you think you first saw a reactive transport model in this room? Was it yesterday? What do you think? I might be wrong. I tried to snap a picture of what I think was the first one. Tomas, sorry.
Nobody was paying attention to that.
I think it's on the board. If anybody can think of an earlier one, please put your hand up. This is an interactive opportunity. I think, no, not you. All right. Lifelong students, quiet. Emerging students. There's 3 panels on the board. Do you think the reactive transport model is, I can model, over here? No. Is it over here where our lovely colleague is demonstrating the Peckley number?
Yes.
Whoa, okay, maybe, sort of. I don't know, actually. That's not there. I think it's here. Do you see for just a second he popped that little S in there? It was like source sink term, oh, by the way, maybe we could have radioactive decay, and moving on. Run away. All right, fine. So he gets into this idea of a Peckley number. He's relating characteristic timescales of diffusion and dispersion to characteristic timescales of advective flow. And he might have even said the word Damköhler number. And I was sitting over there. And I thought, perfect. I'll take a picture right now and I'll pick up where he left off. But then, I think this thing has a range of like 1 meter. Then, Kino came along and was like, I got you, don't worry. You don't need to introduce Damköhler numbers at all. I'm going to talk about them quite a bit. And so, thankfully, I don't have to do this again. We know now that you can define another ratio of characteristic timescales. It's sort of the complement or the sister to a Peclet number in a reactive transport framework, where we're thinking about characteristic timescales of some kind of transport relative to characteristic timescales of a reaction, a chemical reaction, okay? And I think we even began to pick up on some of this in our workshops. Maybe, I don't know. I haven't exactly been like orbiting, but I saw a blackboard out in the grass and there was definitely a Damköhler number on there. So some of you guys have been thinking about this quite a bit for the past few days. And so perhaps you've begun to pick up on the fact that even between these two guys and their lectures, we begin to realize that there's a little bit of how should I say this, dealer's choice in terms of how you want to define a Damköhler number. So one aspect that we started to see between these two presentations is that you can think about a Damköhler number as relating a timescale of chemical reactivity to either a timescale of advective transport or a timescale of mixing or diffusive transport. And there's even a little bit of a dialogue about which one is better. The Peclet number, modeled here, will get you in between them all the time. Now, what I wanted to pick up on here is that actually there's another little bit of, I don't want to say ambiguity, but understanding of what we're doing when we define a Damköhler number that requires some attention. So, which characteristic timescale of transport are we thinking about? And what's the other piece in here that's a little bit vague between these two slides? What is this characteristic timescale of the reaction? Can you see it in Tomas's board? It's not explicitly written, but it wants to be. Do you see that reaction? That S is getting put right into that equation, right? So that means that S has to be dc dt. And on the other side here, you've got a C times a somebody, known as a rate constant. So that constant, that K, has to have units of 1 over time. That puts you into a situation where your characteristic timescale, where is he? Right here, needs to be 1 over K. Are we all right with that? And yet, behold, a different chemical reaction, a different characteristic timescale. How could this be? And the issue that we want to start to think about, you've had plenty of introduction to advection, dispersion, diffusion, mixing by now. We don't need to do that. The issue I want to focus on now is that the kind of chemical reaction that you're working with also dictates this timescale of reactivity. So the point that I want to send home, the first one, we'll hit a few today, is that this Damköhler relationship that we're going to use to think, that we're going to use to ask, do I have to? Is it necessary to build a model that balances reactions with transport? Depends on how we want to define the characteristic timescale of transport, what kind of transport are we interested in, what kind of transport are we dealing with, and also the relevant chemical reaction. So let's stick with Tomas for just a second. Kino, we'll come back. Don't worry, you're not done. All right, so we're going to pick up on this idea of a very simple, irreversible first order reaction. This is decay. This is exactly what Tomas had on the board. And just to make sure that we're all feeling real comfy with this thing, I've gone down to very, very simple notation. I want it to be friendly. When we see a transition like this, then what we're talking about is a situation where the change in the concentration of this reactant with time can be described as the loss of that reactant multiplied by a rate constant. And that is equivalent to the accumulation of whatever you're making. As we just said, we kind of just did it in our heads, right? It's really not bad. The characteristic time scale for this reaction is going to be the inverse of that first order rate constant. And it's really easy to solve. It should feel good to be able to solve this kind of thing. Look, bring the t over here, bring the c over there, integrate 1 over c dc. You get natural log, right? That's where the exponent comes from when you move the thing over. And the c naught simply comes from, I need some kind of an initial condition, right? Seems like a reasonable one to say that at t equals 0, c equal somebody that we'll call c naught. And that's it. That's super, super friendly thing to be able to work with. So, what do you think you're looking at here? 3 different solutions to that equation. What could possibly be different between them? K, exactly, very good. We're doing great, you guys. Look, you're all chemists already. Excellent. And you really didn't have any other option, right? You can see that C naught is fixed, okay? Right? We're moving through time. And so the only thing I have left to do is play with K. And you can intuit, I hope, that as you look from yellow to blue to red, you're decreasing K. You are looking at a reactive transport situation, all right? In the limit, if K was super duper high, then anything beyond like here, we really wouldn't care anymore, right? Not worth it. Do I have to? No. You're outside of the scope of where you need to worry about relating those two time scales. K would be too fast relative to how quickly this thing is being advected, or actually reacted. All right? If you're in a slower K regime, then if you're thinking about this as distance along a flow path rather than time, then things are slowing down, slowing down, slowing down, and eventually you might be in a situation where, you know what, chemistry doesn't really matter at all anymore relative to how fast something is moving, either by advection or some mixing process. So we're constantly rolling around in our heads whether or not we need to worry about this sort of thing. This is exactly the same thing that we just said. I've gone super simple with the notation. I've taken it down to steady state. And now all I'm doing is balancing that exact same reaction with advection rather than allowing it to evolve through time in a beaker. Okay, so exactly the same math. The velocity comes over before we separate the dc and the dx, and we do the same calculation. We get the same result, and somebody is staring at you right now. It's that Damköhler number, right? You see him? We better hope we see him. I don't want any units in this exponent. 1 over time times distance, distance over time. Okay, so we've talked a bit about this idea of thinking about movement, advection or dispersion or diffusion along some distance, and the idea of this reaction proceeding from some starting point down to its completion. I promise you this time I didn't vary K. So what's the only thing I could have varied? What have I got left? Velocity is exactly right. From yellow to red to blue, is velocity increasing or is velocity decreasing? Increasing. You got it, right? You can feel it in your heart that if you were flowing fluid through a column and you released a dye, that it's going to go shooting down that column and you could watch it, right? And if the flow is really slow, then it's going to take forever. And if the flow is really fast, then it's going to go screaming through. And somewhere in the middle of this is my employment. This is where we live if we're in a balance between timescales of chemical reaction and timescales of transport. If the transport is super duper fast, be a really good fluid dynamicist. If the transport is super duper slow, be a really good chemist. And in the middle, be okay at them. Okay. All right, good. So velocity changing. All right, you guys are so smart. Now, what if we have a different kind of chemical reaction? Oh boy. Look at the yellow. this guy, versus look at the reddish orangey thing. Which one of them do you think was that decay reaction, and which one of them do you think is this higher order reaction?
Yellow is higher order.
Yellow is higher order. Don't look at blue. Yellow or orange? Which one is first order or which one is second order? It's kind of tough, isn't it? If this were a really big number, I'd agree that it's possible that that yellow is going faster because obviously you're squaring the concentration, but we're starting off here and we're going into lower and lower and lower values. Think about what happens if you square 0.8 or if you square 0.5. That second order reaction is actually slowing down, extended, taking more and more and more time relative to the first order case. Can you see how the characteristic timescales of the two reactions are different? They have to be because the rate constants are different. This thing is 1 over time. This thing still has to give you dc dt, okay? So that's got to be a 1 over concentration times time, which means your characteristic timescale for the reaction must be something like 1 over concentration times time, which is exactly what Kino had on his slide, a 1 over concentration times time. So I guess you must have been working with something second order-ish in whatever you were thinking. Dunno. A plus B goes to somebody. Yeah, okay? So as we're thinking about different kinds of chemical reactions, we're thinking about different definitions of that characteristic timescale. What is the blue thing? It's not going to 0. We're all going to die. No, it's okay. All right, what you're looking at in blue is a reaction that is not advancing inevitably and irrevocably to 0. You're looking at a reaction that is advancing towards some value. You'll see that value has many names depending on who you're talking to. Equilibrium, some solubility limit, some value that defines the end of that reaction. And the key there then is that this reaction is potentially reversible. These are the kinds of reactions that we work with typically when we're working on rock weathering, when we're working on interactions between fluid and rock. Behold, if I start out at 1 and it looks like I'm trying to end up at, I don't know, give me 0.3, then it's going to be 1 minus bigger number. Agreed? So this whole thing is going to be negative, and this thing is shooting down. However, if we started at 0, instead of starting at 1, these two reactions would be like, meh, done. Got nothing to do with it, right? 0, 0, 0. If we start at 0 in this reaction, then it's going to be K. And we're going to come shooting up in this reaction to the same value. So on either side of where you're trying to get, the system can evolve to this final value, which oftentimes gets called equilibrium. And we will see, I hope we'll get to it by the end of the talk, that that's not necessarily a very good name for it. Okay, do not ever do this. It's a terrible slide. Let me explain myself. I wanted you to see just the very simple analytical solution for that reversible reaction. I kind of want to stand in front of it so that you aren't like, ugh. I went back and looked. I gave a talk here in 2018, and I did this on the board, literally. And I had one of these like, does anyone know who Christopher Nolan is? You know, he directs like Inception and all these movies where time keeps going in circles. And I had an Inception moment. Like, am I supposed to redo the derivation again, even though I'm watching myself do the derivation on YouTube on this board 6 years ago? So I decided not to. It's up here for you. It is super duper duper simple. The hardest thing about it is deciding what you want the constant of integration to look like if you're already using C. I spent like 30 minutes on that playing in LaTeX. I finally came up with something that looks like the Campbell's soup logo. Eventually, you will get to this. Go through it in your own time or watch me in the past doing it, and now I'm talking about it now. Okay? And you will find that you get behavior that will basically distribute like this if you're relating that characteristic timescale of the reaction to a characteristic timescale of advection or flow. What is that characteristic timescale? Where did it go? Okay, we can always back up. What are the units on my K in this case? It's got to be, well, if we were relating it to the progression of a reaction, it's got to be dc dt. We've seen that a few times now. But here it's getting multiplied by something that doesn't have units. So that K is going to have to be concentration per time as well. All right, so the third K that we've seen so far this morning. And indeed, when you get to Damköhler land, and there he is right there, it's going to be concentration per time times the distance, and it's going to be distance per time times the concentration, and we're okay. So our third Damköhler number of the morning. Now, what you see in this variation with flow rate or advective transport relative to this concentration is a distribution that goes like this. If I am going super duper fast, there's no time for the chemistry. If I'm going super duper slow, I'd better be a good chemist. Actually, I don't really need to be a good chemist. I'm kind of done, right? Next problem. And in the middle here is going to be the world that we will live in for the remainder of this discussion. And the reason that I want to point this out to you is that it has been proposed that this very simple basic relationship explains rivers. The solute chemistry of major ions dissolved in rivers, some rivers, asterisks. Okay? So this is kind of a little bit of a famous set of papers in my tiny little world where Kate Maher put forward this idea that you could describe the concentration of something dissolved in fluid relative to how fast the discharge is occurring over long time scales. Let's be clear. We're not looking at a storm here, okay? That's an entirely different animal where people will start to talk to you about mobilizing different flow paths. But in general, the inference here is that in the long term, when we're picking up relatively higher flow rates, maybe it's a rainier season of the year, versus relatively lower flow rates, base flow, drier seasons, different conditions, then you're going to see this distribution of solute load that behaves according to this basic relationship between how fast the water is draining through the system and how quickly those water-rock reactions are taking place that pick up these solutes. And indeed, what we do see is that if you look at the chemical composition of average rainwater around the world, it's super dilute compared to the chemical composition of river waters. All right? So, in fact, what we begin to infer is that rivers, watersheds, upland systems, the environments that we're looking at if we were to look out the window now, are potentially behaving like little reactive transport models. It would be nice to be able to describe them that way because it's very simple and predictive. This is an interesting study in which they took the total dissolved solids in a bunch of different tributaries going up to a large river system, and they used geochemical dark arts to figure out how much of the total dissolved solutes in those waters came from the rain versus came from the weathering of rock. And so the message to send home, either in absolute values or normalized so that they all add up to 100%, is that the amount of the water that came from, the amount of the solute in the water that came from the rain is extremely tiny. The vast majority of what that river is carrying in the dissolved load came from chemical reactions between the water and the catchment as that water was draining through the landscape and into the river. And essentially what you're looking at is mass flux. This is the delivery of elements from the landscapes into the oceans, and the vast majority of that is coming from these weathering reactions. People have been thinking about this for a while. Wow, that's an old plot. And you can't read it at all, can you? Behold, down here, we have really, really low dissolved solids, okay? Same as this, really, really low total dissolved solid. Not a lot in the water, kind of dilute. Don't drink it, but kind of dilute. As we start to go up on this y-axis, what they note is that we go from something that is primarily made out of sodium and chloride towards something that becomes much more proportionally full of base cations like calcium and bicarbonate. Then we turn over and go the other way. What do you think? What do you think this part of that evolution is? I heard it. Say it louder. Dissolution. Dissolution, yeah, okay, so rainwater, weakly acidic, dilute rainwater is interacting with rock and it's picking up base cations. We're converting something that was mostly CO2 or closer to CO2 dominated in terms of the carbonate system, and we're converting it more towards bicarbonate. We're increasing alkalinity. We're putting more carbon into the water. So if you are interested in things like enhanced weathering, or the capacity for rivers to actually move carbon off of the landscape and into the oceans where nominally it might be more fixed, this is exactly the kind of thing you want to try to understand. What do you think happens up here? We go back to rainwater. No, this thing has super high TDS, right? We heard John the other day, yesterday, talking about the Dead Sea. The Dead Sea would definitely sit somewhere up here. So eventually you take on enough of this total dissolved load, and in addition you get into conditions that are more and more and more evaporative, and you begin to precipitate or concentrate some solutes into the water while others are coming back out again. I love this very, very old plot because for me it's almost like you can see geochemistry at a global scale in the rivers as they evolve from something that's dominated by rain to something that's dominated by rock, this transition being this weathering regime that we all talk about, and then turning back over again and going into something that's even higher total dissolved solutes, salty, salty, salty. Don't sip it, apparently your esophagus will collapse as a result of evaporation and precipitation. Okay, good. So, some setting for why we care about what we're about to do, okay? We're gonna live mostly in here. And the next thing I wanna try to convey to you is that here is, first, super cool, fun to work on, join me. Second, that it's not just dissolution. There's a whole bunch of interactive chemical processes that are taking place in this advancement of water from rain towards something that we would identify more as a river. So how do we do that? We're going to start off with something that's dilute. There's probably a little bit of salt in it because it probably evaporated off of an ocean and then got pushed inland and started to rain out. It's equilibrated with atmospheric CO2, which means it's at a pH between 5, 5.5, maybe 5.7, depending on where you are. It's going to fall on the land surface. What's the land surface? It looks like this. More on that later. It's probably going to pick up even more CO2 as it's working its way down into those shallow layers, because this is very organic rich. See what I mean? There's a whole bunch of organic carbon conversion to CO2. Oftentimes in settings like this, if you were to put a chamber onto the land surface, what you would see is that the land is effluxing CO2 back to the atmosphere, not the other way. And so by the time it gets a little bit further down into something that looks a little less like soil, that's starting to look a little bit more like rock, choose your favorite contentious word. People will critique you no matter what you do. Regolith, saprolite, whatever you want to call it. It's a fabric that's starting to look like rock. It still has weatherable minerals, and your water is ready to do work on this. We're ready for a variety of chemical reactions to take place that are eventually going to convert that rain into something that looks very, very different. What's going on in there? Things like this. Don't look at me like that. You have seen these before and you were into it. You saw super cool presentations already about karst weathering using models like this. We're taking CO2 and we're reacting it with carbonate, and we're making base cation, and we're making alkalinity. It's exactly what you saw on the last slide. This is exactly what we're talking about when we're on the way towards river water from rain. It happens through a variety of different reactions of this type. This one is anorthite, I think. How'd I do? Excellent, nobody knows. It's anorthite. All right? It's a feldspar, it's a silicate. It has aluminum and silicon in it, as well as some calcium. It's reacting with the same sort of weakly acidic fluid. It's releasing cations. Uh-oh. And not everything is coming out. So here's where it starts to get a little bit interesting. We're also forming new secondary phases. Don't be mad at the chemistry. If it didn't do this, you wouldn't have soil. Okay, we're converting something primary, bedrock, into something that looks more like these shallow layers. This is a clay. Its name belongs to the clay mineralogists. It depends on exactly how it's ordered and structured. This particular one that I looked up was called holoisite. Then I looked up kaolinite in another set, and it had exactly the same stoichiometry. I will say no more. All right, another example of a similar reaction, all right, with another type of feldspar. And again, we're releasing some but not all of the solutes into solution. Some but not all of the solutes are leaving. Some of them are forming new building blocks to sustain this watershed, this ecosystem. We would like to be able to model this. And in addition, let's not forget that there's also this theory put forward that the way in which the watershed exports all of these solutes is actually a reactive transport model. So this seems like one of these situations in which it's worthwhile to try to build a predictive forward framework that would allow you to say what's going to come out of this watershed. Challenge accepted. It'll keep you busy for the rest of your life, trust me. So what we're going to see in the next little piece, if you will, of the presentation is a little bit of fun in answering a very simple question, and that is, what the heck is C? We've been talking about it for days. Were we talking about carbon this whole time? I don't think so. I think there are other elements in the periodic table. Can we ignore them? That would be nice. Not always. Sometimes, absolutely. Absolutely. I will say that I have a great fun. If we get to it, if there's time at the end of the talk, I'll show you something that we've done recently that falls back to this generic C, just because I wanted to try to think about how to embed it into a transport framework that hasn't really been done in major reactive transport models yet. If we get there, we'll do it. But for now, we're going to ask a very basic question. How do we go from this sort of generic, not carbon C to this thing? When and where it's necessary. Okay. We all right? Everybody take a nap. It's chemistry time. I'll tell you when to come back. It's going to be okay. I heard that. All right. You do not have to be a chemist for the next few slides. You do not have to be a chemist. I promise you. What I am going to do right now is try to show you that chemistry is actually something that can be embedded into the same mathematical frameworks that you're used to working with in a pretty simple way, and then you can use it. All right? So put all of your chemistry concerns aside. I chose a few equilibria. There are more. There are so many more that it will keep you busy for forever. All right, so this is just a few of them. Okay? Ever so brief reminder, if you're sitting there right now going, oh God, is it reactants over products or products that I don't remember? It's okay. Products over reactants. The little a means activity. For now, we're just going to use concentration. Good enough. Look it up if you want to think about the difference between them. Each one of these constants, these coefficients, is defining a fixed state at which the distribution of concentrations or activities between these products and these reactants is equilibrated. Okay? That constant, asterisk, constant is dependent on temperature and pressure. Don't worry about it for now. That constant means that you don't necessarily always have exactly the same concentration of those products and reactants, but the combination of them, that is the product of these two up in the numerator divided by whatever the denominator, that whole thing is equilibrated when it reaches K. So there's many different versions of concentrations of these species that will give you K. That's kind of what we're dealing with, right? If you want to manipulate them, for example, if you want to add this one to this one, then you could flip this guy around, and when you add it together, because we typically keep these K's in log units, it's really easy. One to the other, whatever. That's the end of the chemistry for this lecture. Okay? I promise, I really mean it. That's the end of the chemistry for this lecture. What we're going to see now is how to manipulate this in a way that works for the types of models that we're trying to build. Okay. Do you see how the way that these reactions are written, there's some kind of common players over here? You see what I mean? They may not always be written that way. If your professor is evil, they won't write them that way. They will make you think about how to write them so that they're nice and orderly like this. But here, what we have is a situation in which we have a whole bunch of stuff, and over here, we have what looks like kind of the same thing again and again and again. So just, very qualitatively, is it possible that we could actually make relationships between these that allow us to avoid the necessity of having to write out 7 different advection, diffusion, reaction equations? That would be nice, right? I don't really want to do that. There's 7 species here. I've got to track all of them, and they're all related to each other. So I'm going to take this sort of common set that I keep seeing again and again. We'll do it more formally in a second. It's okay. All right? And I'm going to try to describe the rest of the species in my system just using them. This is from Morel and Herring. It's called a tableau method. I used to think I sounded super fancy when I said, I am using the tableau method. And then I came to France and realized it means table. Here we go. CO2 is going to be, just follow me, made out of 1 hydrogen, 1 bicarb, and it uses a water. You don't need to know any chemistry at all, right? You don't need to know anything. You're just following this. It's like you're baking. Apple plus flour equals Pop-Tart. You're fine, okay? Next one, bicarb. It's consuming a hydrogen, -1. It makes, that's carbonate, is making a bicarb, 1, okay? CaHCO3, all right, are we getting bored yet? It's super easy. It uses a bicarb, or it makes a bicarb, it makes a calcium, we're good. This is the end of my capacity to animate. OH uses up an H+, hopefully makes a water. Okay, and we're good. All right, now, why did we do that? Other than to make Pop-Tarts. What we're going to do is we're going to look at these creatures and we're going to sum down the rows. Okay? Or the columns, excuse me. Imagine, if you want to, that you could also write the individual species down here too, but it's really boring. It would just be ones under the category. So here's the first one. There's the total calcium in my system. There's the free calcium, and there's that one species that it's involved in, okay? This is a nice thing to be able to describe. Why? Because this total calcium is the number that I would actually be given if I handed a water sample over to a lab and said, can you please measure calcium for me? Total calcium in the water. Okay, next one, hydrogen. It's the hydrogen itself. I pick up a CO2. I have a negative on the carbon. Yeah, CO2 negative on the carbonate, negative on the OH. We're okay. Last one, the bicarb, or total carbon in this case. I've got the bicarbonate itself. I've got the CO2, CO3, and CaH. That's it. That's it. These principal components, or primary species, or basis species, contain within them all of the information that I have that relates all 7 of these species to one another. So, what I want to say to you, if you've zoned out, come back. What I want to say to you is, in modern multi-component reactive transport software, the vast majority of it, we do not advect or diffuse chemical species. We do not transport chemical species. We transport primary components. That's how they work. Okay? Now you know. And when you set up one of these models and you have to put in concentrations for your water, you're putting in total concentrations. The model is going to go back into the dark arts of itself and figure out all of the individual species concentrations, and it's going to do it this way. Are we all right with that? That's it. That's how chemistry works in the types of models that you've probably heard about. The geochemist's workbench, Freak-C, Tough React, Crunch Flow, High Tech, help, Min3P. All of them. You have another favorite? No. I don't like any of them. All right, just for funzos, I thought I would show you a couple more steps of how this calculation then works. Okay, and the reason that I'm doing this, and hopefully this will be recorded and you could go back on your own time and try it out, is that in very few lines of script in your favorite scripting language, you can make your own geochemical speciation model. And I encourage you to do it because I think it'll demystify a lot of what people kind of turn into groaning when we start to talk about this geochemistry. You don't have to be a chemist. It's really just a pretty straightforward matrix manipulation. Okay. Oh my gosh, what did I do? All I did is I took those total concentrations and I subtracted them over here. Come on, that's a pretty good idea, right? Because now I have 3 functions. I have 3 principal components, and I've set them equal to 0. I need the roots of this set of functions. Is that starting to sound familiar? Okay. Furthermore, I know how to define all of these other species because I know how they're related to my primary components. So, no mystery whatsoever. I'm going to take this thing and I'm going to plop it in there. And I'm going to take this one and I'm going to plop it in there. And that's it. Now I have 3 functions. I need to find the roots of those functions. And they're all in terms of these 3 primary species. You know how to do this. This is just Newton's method, okay? So the only thing left to do then is to just set up a little calculator that basically says, I'm going to take a guess. So the software that you use when you try to build reactive transport models is doing exactly this. You specify the total concentrations, U1, U2, U3. The software says, okay, I'm going to take a guess at how they must be distributed as the rest of the individual species within this matrix. Then it's going to evaluate the value. It won't be right the first time. It's going to take the slope to the tangent to the curve or the derivative at that value and go shooting back down to 0. Typically, if things are going well, if the functions are smooth and differentiable and well behaved and you've taken a reasonable guess, then wherever you land on that origin on the derivative is going to be a better guess than the guess that it took originally. Then you're going to take this value and evaluate the functions all together, and they're going to come back up to this. And the difference between 0 and this residual, is once again up to you. Good enough, done, get out of there, or absolutely not. That's not even close to good enough. This is unacceptable difference from 0. So then you'll take the derivative, boop, back down to the origin again, and you can see with your eyeballs that it's going to get good pretty quickly, right? That's Newton's method. And we're just doing that for a bunch of different functions all together. It means that you have to write a little script that includes these functions. It also helps, although a lot of software will do it for you now, if you go ahead and write the script such that it contains the partial derivatives of each of these functions with respect to each of your primary components. If your professor is evil, she will make you do it yourself at least once. Try it. Why not? Here, I'll do the first one. Okay, I got to take the derivative of the first one with respect to calcium, so it's going to be a 1. And bicarb over K3. Oh, I can definitely do the next one. It's 0. And the next one's not so bad. It's going to be calcium over K3. This one, 0. That one, and I'm going to run away now. Oh, okay, yeah. So I put the first one in there. Try it. And once you've got this Jacobian set up and you've got the functions set up, it's like 5 lines to tell the thing to do this little algorithm. And you have built your own freak C. That's what it does to come up with the full distribution that simultaneously satisfies this criteria for all of these species. Give me just a second longer and we'll look at pretty watershed pictures, okay? But I want to be sure it's clear to you that I kind of tend to present this, I've seen a lot of people tend to present this as a little bit of a party trick. And I just want it to be completely clear that it is actually coming from something much more formal. Here's another set of equilibria that can, now see, you're getting good, aren't you? Can you eyeball it now and kind of feel what you think those primary species ought to be? Right? Maybe this time we're going to work in terms of CO3. We've still got a calcium, we've still got a hydrogen. Now, I haven't declared whether or not these guys are equilibrium relationships or whether these guys are actually time varying. All right, we saw the reversible, don't look at me like you don't know what I'm talking about. We saw the reversible reaction at the very beginning of the talk, right? The K parentheses 1 minus C over C eq. We could easily write any of these that way. So it could be a rate-limited reaction, or it could be an equilibrium. So as we start to set these things up then, we know that the consumption of this guy is going to go as negative R1, whatever it is, and on and on and on, and you can relate all of them to one another. The point I'm trying to make then is that if you just put this into a notation that's, for one thing, much easier to enter into any of your favorite algorithms, but 2 is just sort of a nice way to keep the books, then you could write out something like this. All it's saying is here's an identity matrix. That means that this first row is going to pick up this guy and 0 out the rest. So I've got the change in concentration of this thing. And then I'm going to come over here equals 0 R1, 0 R2 and minus 1 R3. Let's hope that's true. Where is he? He's there, and it's minus R3. Okay, so you can read the matrix. It's no big deal. Now, this is the sort of system that is ripe for being minimized. There's a variety of different ways to kind of come at that, but essentially what we're trying to do in this case is we're trying to make this matrix as simplified as possible. Gauss-Jordan is the method. Maybe you've heard about pivot points, all this sort of formal ways of manipulating these kind of matrices. All that we're really doing is we're trying to take everything below this like 1, 1, 1, 1, and we're going to try to convert it so that these are zeroed out. And in doing so, it means that you have to kind of manipulate this one. So for example, if I want this calcium to equal 0, right now the calcium equals R1. So it would help a lot if I could pick up one of these because it's a minus R1. So what I'm expecting when I do the manipulation is that it's going to go 0, 1 because I want to, wait, no, 0, 0, 1 because I want to pick up that guy and then the rest. So here's the manipulation, and yeah, 0, 0, 1, and then the rest. The point I'm trying to make, I'm almost done, calm down. The point I'm trying to make is that when you go through this formal manipulation, you get the tableau back. Morel was not just pulling a party trick. I learned last night that Morel is not to be trusted on a tandem bike, but he can be trusted with matrix algebra. The point that I am trying to make to you with all of this, then, is that the principal components, the primary species, come from this reduction of this matrix, okay? And what that winds up meaning is that I have these relationships, very simple, for the individual species, and then the remainder is actually my mass balance. These total concentrations. It does not matter, and I haven't declared yet if any of these are equilibrium or if they are time varying. It will make a mixed differential algebraic set rather than just a bunch of algebra, but you solve it the same way. And that's how this works. This is the next thing that I want to say to you, and we're out of here. Okay? Well, not really, but we're back to pictures. I hear it a lot. I've heard it a lot this week. I don't really do chemistry. Okay, fine, I'm not really sure I do chemistry. But when we're in this context, when we're thinking about flow and transport in porous media, and we're getting into reactive flow and transport, when we say something like, I don't really do chemistry, we're kind of saying, I don't really do linear algebra, which isn't necessarily something that you want to share, right? Okay, so my message to you, if I could give you one message this morning, is don't hide behind I don't do chemistry. It's just matrix manipulation. You don't need to do chemistry. And this is exactly how this is going to work in these reactive transport models. You're going to take a time step. That means that you're going to transport the primary species only. When you're ready, and that is its own conversation, when you're ready, probably in the middle of the time step, otherwise known as operator splitting, you're going to stop. You're going to speciate out everything, exactly with the algorithm that we were just talking about. You'll do the time-dependent reactions. You'll pull everything back up together again into the new primary component values, and you'll go on for the rest of that time step. And then you'll do it again and again and again and again. All right, and that's how these models work. I was going to make you look at a database. I don't think we have time. Okay, we're back. Part 3. Okay. All right, so I am sorry. That is probably one of the driest things we can possibly talk about first thing in the morning, but I really, really hope now you can see or appreciate a little more about what we're up to when we look at these different elements. Maybe you can even start to see some good candidates for your principal components. Maybe you want to use silica. Maybe you want to use sodium. Actually, you'd better, because you're building these minerals out of them. or these minerals are releasing them. So those are going to have to be some of your primary components. Maybe you can actually already look at this now and see that there's some redundancy in here. I've got both CO2 and bicarbonate. I'm not really sure I need to do that. On the timescales of rock weathering, I'm pretty sure those two are in equilibrium with each other. I really only need one, and then I know them both. And that's how the whole thing works. Okay? Not a single question. All right, so we did a little bit of a thought exercise understanding the Damköhler number in a very simple way when we were back in the land of C. Don't we miss C? That lovely C that didn't bother us with matrix algebra or multiple components. Now we're going to do the same thing, but I want you to understand that what's embedded in the models I'm about to show you is a lot of chemistry, both in terms of the aqueous distributions and how they're interacting with these multi-element minerals. And now we're back to looking at the minerals themselves. So what happened? Kate Maher happened. She built a model in a multi-component geochemical reactor transport setting. She's applying rain to the surface. She's allowing fluid to drain into the domain. And what we are looking at here maybe is a little different than what we've thought about so far this week. We're not looking at the fluid, we're looking at the mineral. We're looking at the mineral itself, and we're actually looking at how much of that mineral is there as a function of depth. So we're going over much longer time scales, rock weathering time scales now. We're running the model forward through them all, and what do you see? Are we gaining this mineral or are we losing this mineral? We're losing. We're looking at a weathering front, right? This thing is going down, down, down. Is this thing at steady state? No. What happens when we get to the bottom? Doom. I don't know. No one would run a model that long. Good enough for now, okay? 250,000 years. And what's happening is we're eating away at that primary mineral that wants to dissolve. Would you think about this thing as being limited by how fast the reaction is going? Or would you think about this as being limited by a transport process? What do you think?
Solubility?
Solubility, yeah, so we're hitting solubility here, right? You can see it. There's no more variation in the mineral. If I sped up the reaction, I think I could make those fronts a little bit sharper, which means that they would hit solubility a little bit shallower at any given moment in time. Do we agree with that? Yeah? So if at the end of the day what I want to do is sum up the mass of stuff that's being evacuated from this system, I would say my best way of doing it is to speed up the flow, right? If I speed up the flow, I'm going to push these reaction fronts down a little further. I'm going to push reactive water a little further into the domain, but not by much. This thing is reaching solubility or equilibrium or whatever word you want to use so quickly that it's really a matter of transport in this particular setting. The flow is what's dominating this thing. And I would have to push on the flow really hard to be able to stand down here and hold a cup out and collect the water draining out of this thing and see any variation between flow and solute concentration. You see what I mean? This is not a situation where you're going to see much in terms of that Damköhler sensitivity in flow rate. You'd really have to go for it on this thing. Here's another mineral. It's another feldspar. In this case, let's remember, hang on a minute, let's remember, they're all tied together. We didn't run this thing and then run this thing, right? These are multi-mineral, multi-element simulations that are all happening at the same time. And this particular mineral, I would say, is a little bit more Damköhler flavored. Can you see how there might actually be a little bit of a balance, a give and take between the concentrations in the water that would be draining out of this thing? Maybe. I mean, it's getting awfully close to vertical, but I think if I pushed on it a little bit, I could get some variability. So something a little bit closer to a balance between reactivity and flow rate in terms of what you're actually seeing as the mass load exiting the system as a result of this mineral. And finally, the other side of the coin, the clay, that is growing in with time, mostly at the surface, because this is where most of the reactive water is solubilizing these readily dissolvable minerals and turning them into new secondary phases that remain in the domain while some of what's dissolved in the water leaves. More dominated by flow, more dominated by reaction. That's kind of a hard one when it comes to a secondary like this. We tend to use the word autocatalytic, meaning that it kind of governs itself in the sense that as it begins to grow in, it's doing so because these guys are dissolving, but as it grows, it pulls material out of the water and therefore sustains the capacity for the water to dissolve more of the primary minerals. They're coupled to each other. So that is this emergence of a soil from rock, simultaneous to the emergence of stream flow from rain. And I gotta say, Kate did a pretty good job, all things considered. Yeah, there's a lot of bells and whistles in these models, but this is the Santa Cruz chronosequence in California. She knew the age was about 250,000 years old. She ran it out to that amount of time. Infiltration is something like 300 millimeters per year. Temperature, average 13 degrees C. Not bad. What's up?
So I'm curious, when you run these like 1D column reactor transport things, what the hydrological boundary conditions are. Like, are you assuming changes in hydraulic properties, or is it all just like vertical and limited by the flow rate that you can get through the bottom line?
It's a really good question, and you can do it in a variety of different ways. This one is very, very simple. It's a 1D column, right? So what you put in is what's going to come out, even if the hydrologic properties vary therein. So, if you wanted to go to a feedback between how much these minerals are evolving and how much that dictates a change in porosity, you can kind of obviously see it, right? We have the mineral volumes for each and every one of these. How that relates to permeability, dark arts. But several options in the code that you can just turn on a flag and it'll give you a cubic law or some other Kozeny-Kármán relationship, and off you go believing that that's something. Yeah, so plenty of opportunity in there. Maybe the thing I can say to you that would be enticing is that part of what these models track is molar volumes of the minerals, which means that you can do a mineral replacement reaction that will actually clog up your aquifer. Or you can do a mineral replacement reaction that actually opens up new pore space even though you're converting one mineral to another, which I think is pretty powerful when we're thinking about things like degradation of a well, cementation.
Okay.
Yeah.
So the underlying assumption here is that this is a reversible process.
Some, but not all. We don't form a feldspar in soil.
Or clays, maybe it is reversible but on a different time scale. So how do you deal with that? Because this is kind of driven by the assumption of equilibrium constants.
It is, yeah.
To balance all the speciation that you have in the system. So is it not self-contradictory that you'll have equilibrium constants that act almost instantaneously? I mean, equilibrium has no time dependency there, whereas some processes may not be reversible within the same system.
It's a good point. So not, first of all, so the question is it contradictory to be using an equilibrium in a system where not all reactions are reversible? The first thing to say is, even if you're using equilibrium, you can approach equilibrium in a time-limited way. And if you put on, if you go read the books and kind of understand what everybody tells you, then you would say, okay, if I am going to approach equilibrium from a state of undersaturation, so I'm dissolving, versus if I'm going to approach equilibrium from a state of oversaturation so that I'm precipitating, I might not want those to be mirror images of one another. And that capability is certainly there, but you're going to have to decide how you want to handle it. Good question. Yep.
So, I mean, I think it was a very basic question, but I'm trying to understand the thoughts. So what we see, I think in the most right one is that I think the hydrogen ion is not penetrating deeper, maybe there is less flow.
The what? I'm sorry?
In the right plot, I think this hydrogen ion or acid or some reactant is not penetrating deeper, and in the middle there must be flow and it's penetrating more deeper.
Everything is the same simulation. The flow is the same in all of these. This is all simulated at once with the same flow rate, the same boundary conditions. What you are looking at are different minerals. Each of them are subjected to their own relationship between how reactive that water is and how quickly they're going to dissolve or precipitate. That's the multi-component trick. All right? So when you see this thing moving down, 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 and this thing moving down at what looks like faster rate or more advancement, what you're seeing is a mineral that is less weatherable versus a mineral that is more weatherable for the same water.
Yeah, but it's being reacted to the more deeper regions, right?
Say it again.
I mean, the reaction is going actually to more depths, right? Mm-hmm. In the middle one is so it's like, I think even per meter it is being affected, but for feldspar it's I think 2 meters and then it's saturated, right?
Mm-hmm. Yeah, that's because of the properties of this feldspar versus this plagioclase. All the same water. It's a lot to get your head around, isn't it? We started off with these little what could be varying? Rate constant, velocity, and now you're kind of having to do the same thing, but you're having to do it with many, many, many different elements in play, many different minerals in play in a fluid that's interacting with them. So that's how we tend to think about building these reactive transport models. Don't worry, I'm almost out of time. You're going to live. Let's go outside. We made it. The last and final piece of fun for us today. I wanted to put forward to you kind of what I've been thinking about recently. What you just saw, even though I've been putting it in the context of rock weathering reactions, these sort of multi-component numerical reactive transport models, they really, I think, largely came out of a legacy of contaminant hydrology. Can you see how pretty complicated chemistry might be involved in the remediation of contaminants, particularly if those contaminants actually form mineral phases, or if they stick to the solids that they're surrounded by, or if it's time varying, or if you're putting in some sort of additive or something like that. So there was a lot of contaminant hydrology legacy, which to this day I would say still propagates into how these models work. And so I have been having an absolutely delightful time, on the one hand, asking, how do we think about these natural systems as reactive transport problems? But on the other hand, how do we challenge what we currently have at our disposal in these models in order to be able to do a better job of handling these systems? I think you can probably think of a lot of different things that you might be interested in, right? The variety of flow paths that you might imagine as an ensemble of what shows up in a river. It's not just a 1D reactor. Okay, when you peel away the surface in these upland watersheds now, what I want you to see is a reactive transport problem. Again and again and again, you're seeing something that looks more like rock, and it's turning into something that looks more like soil. And it's happening because fluid is infiltrating and draining, and along the way it's making these conversions. And at the same time, in these upland systems, the bedrock is being exhumed slowly, 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 and exposed to this oxygenated, photosynthetic, reactive, awful surface known as where we live. That's the critical zone. Okay? So how do we begin to think about these systems in a reactive transport framework? The thing that's got my attention at the moment is this. In these upland low order systems, we know that water is stored in the rock. You would be shocked, I was shocked, at how much water a hill can hold. It's a lot. And that water is the same water that is then mediated or filtered, if you want to think about a catchment as a signal filter, into what we see as runoff in the streams. That same water is the supply for deeply rooted ecosystems. This is largely work from my colleague Daniela Rempe, where she's done an absolutely marvelous job documenting how large forest ecosystems survive periods of water stress, drought, Mediterranean climate, because they are accessing this water stored deep below soils. So the ecosystem is in play in this water as well. Daniela and I have been having a wonderful time playing with deep instrumentation into the vadose zone, in which we're looking at the distribution of gases. And what we've found, at least in one place in particular, is that there's a lot of CO2 down there. What you would classically think about is sort of that organic rich, maybe 1 meter thick soil horizon where all of that meteoric water picks up extra CO2 and then goes further into the rock and does work on it because of that. That CO2 is meters down, and there is a lot of it. So these ecosystems are essentially injecting reactive potential below the weathered material and into the primary minerals where this weathering potential can be utilized. And at the same time, these hill slopes are essentially, as we said, exhuming or bringing these reactive materials up into the shallow layers where they're exposed to all of this life and meteoric water. So this must be the kind of place, this must be the location where we should see this dynamic between the rate at which fluids are draining or moving through the system and what we see as solute chemistry in the streams coming off of these landscapes. And yet, I kind of cheated. The one that I showed you before, where it was so cool and it definitely showed that Damköhler relationship, they're around, but it's not universal. I would say it's not even necessarily normal for these major ions, the ones that tend to come from interaction of water with rock. It tends to be the case in a lot of low order streams that they are so-called chemostatic or close to chemostatic, meaning flow rates can vary by orders of magnitude, and yet we just don't really see much in the way of dynamics of the solutes in this system, and it drives me bonkers. I don't like it because I like to build reactive transport models. I can see the reactive transport model screaming at me. And these systems, I can see the rock getting converted into soil, and yet I'm not seeing this flow relationship that I thought I was supposed to. I'm not the only one to be bothered by this. I was so bothered by this that I sent my graduate students out into a terrible flood in this particular stream. It was an atmospheric river event. An untold amount of water fell into this small catchment, and they were out there in the middle of the storm. The entire storm they stayed collecting water samples for me. If anybody's interested in, no. And so in this just absolutely unbelievable event, and here, yes, we are in a single storm. We're not looking at long-term averages anymore, and still you can't push the thing out of this basic static sort of behavior. Okay, they turn a little bit, but come on, that's nothing compared to the range and discharge values. How do these systems stay so stable in their chemistry with all of the internal dynamics that we know are happening? I don't know. I'm not really sure anybody knows. We're all kind of chiseling away at this in our own little ways and means at the moment. I will say that I think one thing that is a bit of an elephant in the room, if you know the saying, imagine there was an elephant right there and we've been ignoring it the entire time. That's what elephant in the room means. One thing that I think is potentially at play here is that in this sort of, simple reactive transport, flow for time, chemical reaction timescales versus transit timescales, that's just kind of missing. Certainly missing in the multi-component models is a more rigorous treatment of the ecosystem and the ecosystem effects on solute chemistry. That has just woefully been missing in this kind of modeling framework. I'm getting recorded. I'm sure somebody out there is on it. But in the major multi-component software, it's not something that is available typically. You can do microbial reactions, certainly, and there's been a lot of work on that. Again, I think because these microbially mediated reactions have for a long time been utilized in contaminant hydrology. But in terms of how ecosystems access water and solutes that they need to live, maybe not so much.
Can I ask?
Yeah.
Yeah, I don't want to be antagonistic.
Yes, you do.
I'm trying to frame it. I haven't heard a word in your presentation so far about plants, except maybe the last sentence that you just said. And that bothered me a lot because the agents that would basically drive reactions, accelerate or slow down, are probably not only what Kate was modeling there in terms of the chemistry itself.
Yeah, absolutely. So Corey Lawrence did a follow-up paper to Kate's model in which they looked at organoligand complexation as a driver of weathering. I know, I see you shaking your head.
It's not the chemistry, it's not the biology.
The biology is different, yes. And you'll be happy to know that I think I have 8 minutes left and we're going to do plants.
Okay.
I didn't rig that, I promise.
She told me to ask you.
I did not. All right, one more motivation slide and then we'll get into it. Once again, geochemical dark arts, but Friedhelm and colleagues went out into the world and they tried to estimate the ratio of the flux of different elements coming out of a catchment relative to the flux of those elements through the ecosystem. Does that make any sense? So like 1 doesn't really mean a lot on this scale, somehow they're balanced. But in general, what I want you to see is that some elements, like sodium is sort of like the poster child for ecosystem does not need, ecosystem does not want, has a very low sort of ecosystem cycling to dissolved export ratio. In other words, if sodium dissolves out of this rock, the ecosystem would sort of be like, bleh, I don't like you, go away. So you could think about sodium as being like rinsed out of these landscapes, not desirable. Whereas in comparison, if we start going out to something like silicon, which a lot of people are surprised to hear this is actually necessary and used in primary productivity, then you start to see something where, at least in some environments, in some settings, it seems to be more held on to. And then you get into the big ones, like, you've heard NPK before, this is K. This thing is absolutely necessary. Potassium has to be there in order for this vegetation to thrive, and it's really strongly retained. So I think at a big picture scale, rivers ought to be getting pretty darn influenced by the ecosystems that are utilizing the water that's draining into them. Okay, we're going to go back to C. What's C? I don't care. It's not carbon. It's just C. Okay, we're going to fall back to a real simple representation of chemistry because I want to try to think about what it would look like. Happy? I want to try to think about what it would look like if we could very simply represent in a long time scale, super simple, what the trees, what the ecosystem is doing both to the water balance and to the solutes that are in that water, okay? So we've seen this guy 1 billion times now, changing concentration. It's an advection reaction equation, diffusion, Advection, this is our old friend now, right? We've been friends for a long time. I didn't use eq I use C-lim just because I really do think using the word equilibrium makes like the potential for someone to like rise out of the ground and yell at me about, you know, thermodynamics, and I just don't want that. There's one more term here. This is going to be our friend. This is going to be some metric for the water that's taken. It doesn't go to the stream. It goes back into the ecosystem, transpiration, and the concentration of what's in that water. Okay, I'm going to do a bunch of simplification. I'm going to go steady state. I'm going to bring this thing over there, okay? Now watch me here. Two things happened. I've decided that that T is going to be represented as, essentially you could think about it as like a deceleration. There was an initial velocity at the surface, there was an initial flow rate and infiltration rate, and as we go down into the subsurface, it's slowing down because the roots are taking some of that water. So that puts this thing in play, and now because Q is changing as well as C, I can't just pop a velocity out and divide it over and do the Damköhler thing. I can, but in this case, we're going to have to deal with both of them changing with distance simultaneously. Porperato did some things like this at some point. This is a little bit different. I'll show you.
Why is the sink time, let's say, proportional to dQdz? Can you...
Sorry?
So when you said that T of Z was dQdz, so you're treating like as a drag term or something?
Like a drag term, yeah, because the...
Why is it like drag?
Yeah, so think about there's a flow rate, and there's roots discretized with depth, and the roots are taking some of that flow.
I'd expect proportional to Q, right?
It's going to decelerate with depth. So it's a slowdown of Q.
But that's the product of your steady state assumption.
Exactly.
So what is there any difference between this term, the C dq by dz, and then gamma cz dq by dz? I mean, except gamma, right?
Sorry?
Is there any difference between this?
This one and this one?
Yes.
No, they're the same.
Why?
Too cute. You'll see. It's going to come out. So there's a Damköhler number. There's the capacity to track how much water, or as we're decelerating, how much solute is taken out with that water and taken back up to the surface. Okay? This is the difference between what we're doing with the water and what we're doing with the solutes. When the water goes back up to the surface, it's gone, back into the clouds. When the mass of these dissolved solutes comes back up to the surface, it's still there. Cute, huh? What are we going to do with it? What do we want to call it? We have this new mass that lives up in the surface. It's a tree. And eventually it's going to be able to go back down again. So the first thing that we're going to do is we're going to decide how much, when the water is taken as a function of depth across the profile, does the plant hate it? Sodium? Bleh. Does the plant not really care? Or does the plant really, really need it? Okay? Now, we take the mass that got put back up to the surface, and in the most crude way possible, I'm very sorry, we just put it back onto the surface again. Instantaneous resolubilization. We will make it better later. But for now, we just mix it right back into the surface, and so the boundary condition is actually internally defined. It's cute. Come on. And if you're willing to let me make an assumption that that deceleration is linear, why not? Then it solves. It actually solves, like closed form solves, which is fun because we get to make little cartoons. So, this is the end of the talk. This is a world with no trees, no plants, okay? Just as a point of reference. It's not really fair to compare them directly. These are 3 different scenarios from that model. They differ in the following way. One of them, blech. One of them, and one of them, yum. That is literally how it's written in the script. Can you tell which is which? What do you think? Okay, if it's bleh, then no matter what happens in here, you're never going to take any back up to the top. Don't want it. So that has to be zeroed out. Okay, so that has to be this one. If it's passive, a lot of things could happen. It kind of depends on the chemistry that's happening inside that weathering profile. But if it's active, then my guess would be that you're going to put a lot back up to the surface. And that's exactly what we see out of the model framework. Okay? It gives a really interesting set of behavior because once you get below that depth at which the roots are taking water, then you basically, the way I think about it is like you snap back. You go right back into that abiotic world where it's just a balance between weathering reactions and how fast the flow is moving. But now how fast the flow is moving is not the same as what I applied at the upper boundary. It's what's left. So that actually allows you to give a relationship between flow and chemistry that you would see draining out of this profile. Very crude, but could be cast in terms of what you would see in a stream. And this is the fun part, I think. And that is that for bleh, it's possible for the ecosystem to push the concentrations that are being exported above what would otherwise be their thermodynamic limit. Ecosystem regulation of base flow chemistry, not thermodynamic regulation of base flow chemistry, or at least in tandem. Get out of my watershed. Passive can do a lot of different things, but when you have an element that's very strongly required by the ecosystem, in fact, there can be conditions in which it's extremely difficult, if ever, to reach what should be that value of what's being exported. And in a very coarse way, if you look out over the world in river chemistry, if you take sodium, which isn't very tasty, and you calculate what the silicon and the potassium should be relative to the sodium, just given the assemblage of the rock that you're dissolving, it's missing. So maybe some of the dynamics that I've been looking for, that many of us have been looking for in this river chemistry, has an overprinting to it that's ecosystem regulated. And the thing that I just showed you, I would say, is not in any way some profound new advancement in terms of how ecosystems function, but what I can say is that it is something that embeds nicely into an RTM framework. So maybe it's a way forward to start thinking about multi-component behavior. I can't thank the people that have contributed because it would take another hour. So I thought I'd thank the organizers. So I appreciate your time and letting me come out and visit. Thank you.
Thank you very much, Jenny, for this great lecture. And more questions? Yes.
Hey.
Thank you so much for a great lecture. So I saw oftentimes that you are not putting in dispersion terms. So I'm just curious how your community views the importance of dispersion in this. Yeah.
Super important. I just kind of thought you were going to do it. You're absolutely right. I mean, I chose to make a lecture that was looking at sort of big scale watershed behavior. I should say that these models incorporate some amount of diffusion and dispersion, whether you like it or not, right? Because there's numerical effects that cause diffusion and dispersion. On top of that, you can certainly add in what you think is appropriate, and you can make it different in the longitudinal and transverse direction and all these kind of things. It depends on what your problem is and what you're trying to solve. Most of the output that you saw from the multi-component models here was a software called CrunchFlow or CrunchTope. And I would say that Crunch is very good at that kind of thing, at least for a multi-component reactive transport model. You can take it all the way down to pure diffusion. It also embeds the capacity for so-called Nernst-Planck effect, meaning that you can diffuse along a charge gradient as well as along a concentration gradient. So people have thought a lot about this. Christoph Tornasa at Orléans is a big name, I would say, in this field of multi-component diffusive work. Yeah. Sorry.
Okay. I really liked what you were showing at the end with plant uptake for things that they liked versus things that they hated. I don't think I understand the movement component. How would something they hate end up making it to the surface without uptake versus something that they like is really going to the surface, or is it just disappearing within the plant?
Okay, so this part? Yeah, so it's a term in the equation that is going to sort of work in addition to the normal TST dissolution law that we've been doing for an hour and a half now, the reversible reaction. So if you were in an abiotic world, you would start flowing and you're going to start increasing because you're dissolving. If you're in a biotic world in which as you dissolve, the water is being taken away and the solute is being left behind, then you're going to concentrate even more. Does that make sense? And the water that's being taken away doesn't have any of the solute in it. It got left. And so that water, when it goes back up to the surface, is dilute, which means that you don't have anything in it. Does that help?
Yeah.
And exactly the mirror image for something that is really wanted. The crazy thing is, a nutrient can actually be so concentrated at the surface that you could actually begin at these shallow layers already oversaturated with respect to a mineral phase. Meaning that the action of this ecosystem could potentially be to allow the formation of mineral phases in these shallow layers because those solutes are being concentrated, but it would have to be the same solute that's also building a mineral, which is why I think this is screaming for that multi-component treatment, which is one of the things we need to do.
Very nice presentation.
Thank you.
So you showed the system of equilibrium reaction with carbonate bicarbonate calcium.
Yep.
And you perfectly showed when we have like equilibrium reaction with K, we can solve the concentration, get the concentration with those matrix. So I was wondering, so let's say if we have reaction rate constant
Yep.
for each equilibrium reaction, so if I'm interested in get the concentration over time, with the constant reaction K. So how complicated would it be to get the concentration? Because what you showed is in the steady state, right? So
no,
for example, we have finite constant reaction rate constant. How complicated would it be to?
It's a good question. It's not too bad. When I put up this more formal matrix manipulation, I was trying to make the point that that was done in a way that was generic. Meaning that I hadn't declared equilibrium or time-limited processes yet. So nonetheless, you can go through that reduction of the matrix. Nonetheless, you can pull out your primary components. Then, do you remember that step where when we wrote out the primary components, we subbed in the information so that they were just in terms of themselves? You can sub in a kinetic rate law instead of an equilibrium behavior. Now, you're going to have to treat that rate law, which means that in your time step, you'll have to solve it. But the general approach is the same. It becomes a mixed differential algebraic set is what it's called, but it'll work with the same approaches. I just thought that maybe we'd had enough by then. There's an old RIMG, Reviews in Mineralogy and Geochemistry book chapter from 1996, Stiefel and McCory, that does all of this. And it's one that I go to a lot. Thanks.
Only if there is no students.
Any more questions from the back?
Danny.
No, I was saying only if there are no students asking. So I have a comment and a question. You can. So one comment is that based on this theory, it would make sense to link these mineral fluxes and mineral partitioning to soil formation. And so you can look what's in the original rock and what's deposited in the soil over those timescales to actually calibrate your thinking.
That's tau. We do that all the time.
Okay.
Yeah.
So my question is, why it takes so long? Why did it take so long, in your view, for the critical zone folks to reincorporate plants?
Why did it take, the question is,
Well, let me give you a background. I reviewed the Gordon Conference proposal about 15 years ago. I had no plants in it, and of course I rejected it, and so there will never go to conference on that. And so why do you think it took so long to incorporate plants into the thinking? Because it's great. I mean, I'm very happy with what you showed in the last few slides. Why is that? Is it because the chemistry bias, or?
I can't speak for everybody. I can speak for myself, and I came out of contaminant hydrology. I worked at the rifle site. I was doing uranium reduction for the DOE.
So it's a chemistry background?
It's a chemistry background, I would say, with a little bit of a hydrology flavor, but you know, it was only in the last few years, and because of Daniela, that I kind of decided I had to stop ignoring them. And that's my own personal road, and I imagine a lot of other people who now work in the critical zone realm but have this reactive transport background are probably having similar thoughts. Steve Yabusaki is one name that comes to mind. He's at PNNL, and he's just really, really interested in how to get roots into these modeling frameworks. I personally think that there's a pitfall there in terms of the kitchen sink of parameters, which is why I'm enjoying this. But, you know, I think there are those who are building them in this very, very, like, you know, numerical way, and even having them grow and die, and then their organic carbon becomes part of the food chain and the reaction network and everything. They're getting there, but as to the time scale, I can't, I think maybe you have a better perspective on the evolution of it all than me.
I appreciate your perspective on this, because you've been working on it for a while.
Any questions? If not, thank you, Jenny.